Yeah.
Yes. For question number one, what were your four values for absolute zero? I wrote four values: negative to 17, negative to 88, negative to 90, and negative to 98.
Oh,
And
good.
the average, it came to 286.5.
286. That's really good.
Yes. What is the accepted value for your absolute zero? You said in the lab that it was negative 273
Right.
degrees. All right. In the other questions, I quote you in a few answers, but I don't know if I did the right thing. So, which of your which of your rungs produce the lowest pressure overall?
Oh.
My answer was dry ice at 64, negative 64 degrees and 8.8 pounds per square inch.
Okay, that's good, except we put it in the dry ice.
This is dry ice, produce the lowest pressure overall because it was equalized in boiling water, which gives the fewest number of molecules.
Okay, good. Yeah. So my Zoom kind of kicked out. So
Yes.
you should be saying that the lowest one was when it was in the dry ice and equalized in the boiling water. Is that what you said?
Yes, that's what I wrote.
Okay, good.
And then for the next one, the highest pressure overall, I put the boiling water produce the highest pressure overall because it's equalized in dry ice.
Okay, now those were two questions, weren't there? Wasn't it one question? Where was it? And then the reason that second question was what?
The first one I put which of your rungs produce the highest pressure overall. I put boiling, produce the highest pressure overall, and then why was that?
Hang on.
Yes.
Yeah, let's go back because
Yes.
when you say in boiling water, you've only answered half of it because we put it in boiling water 4 times.
Yes, we did boiling water at 100 degrees Celsius and 26.9 psi.
Yeah, but what they're after here is it can made the highest pressure when it was in boiling water during the run that it was equalized in dry ice. Because remember, we put it in boiling water 4 times.
Yes.
All right. So the part I didn't hear you say was when it was equalized in dry ice. You said it was boiling water, but that only narrows it down to 4 of the 16 times we did it. To be more specific. Yeah.
Yes.
You want to say so you want to say in boiling water during the experiment that we had equalized it in dry ice.
Experiment. But doesn't that part goes in why was that?
Well, it will too also. No, because so the next question is why was that? And you want to say why because, and there's 2 reasons. One, they were moving the fastest. That has to do with the high temperature. And 2, it had the most molecules. That has to do with equalizing it in the dry ice.
So move the fastest. Okay.
Yeah.
And then so let's go back then because then I think I didn't catch that well because I think in the first one I think I didn't wrote it correct if that's the case that you're explaining to me right now. You're saying so in the first one so number 1, number 2, number 3, number 4. So in number 4 I should answer which of your rungs produce the lowest pressure overall.
Right.
I should answer in dry ice produce the lowest pressure overall because it was equalized in boiling water, which gives the fewest number of molecules. That's number Then why was that?
Okay, now let me change that one a little bit. Okay?
Yes.
All right. So there's 2 parts to when it was the lowest. And the second question, there would be 2 parts for why it was the lowest.
Okay, yes.
Okay, so it was the lowest when it was in dry ice during the run that was equalized in boiling water.
Okay, equalize that one. Okay, okay, got it.
Okay, so then when you go on to the next question that says why, you're going to have two reasons why. The first one is the molecules were moving the slowest. That has to do with the temperature. Second reason is you had the fewest number of molecules.
All right.
That has to do with you equalizing it in the boiling water.
Okay, that's it for that question. So the next one will be which of your rungs produce the highest pressures overall. So it was the boiling because it was. Say one more time, please.
Okay, so you should have two things in there. You should say it was when it was in the boiling water and equalized in the dry ice.
Okay. That's it. And then, so then I continue with why was that?
So then you go why. So you're going to give two reasons why. The first one is it had the highest motion or the most motion and the most number of molecules.
Okay. All right. So then let's continue with the next one then. That is which point of each graph will tell the temperature at which you equalize your apparatus. So what I said is what I quote you. I said I said it means I must equalize in the boiling water.
Yeah, they just want you to notice that every time you equalized it, the pressure would go to 15 roughly. It would go to, yeah. And so a vertical line at 15, it's more like 14.7. So a vertical line at about 14.7 would tell you the temperature if you just kind of scanned up and see where it crossed.
Oh, so the answer will be the vertical line at 15 will tell me that because yes, you're right, because when I did that vertical line, it gives me the points like you also said in class 64 negative 64 degrees at 21 degrees 0 degrees and 100 degrees,
right?
And the last one, yes, I feel like you said, I feel I understood and I understand what you said in the last question that is kind of incomplete because it is why it's essential that temperature used in predicting gas pressure be absolute. I think it's missing something, don't you think? It's the Kelvin scale is the only one where the numbers of the scale corresponds to the motion of the molecule. That's what I should write.
Right. And I'll say it again. I think you heard it on the video that last question. The author he doesn't really ask the question as well as he could. Yeah, because I wouldn't say it's absolutely required. I would say it's best to write it in the simplest formula, and the simplest formula means that temperature goes with pressure and you write it on the absolute scale because the Kelvin scale is the only one where there's a direct correlation between temperature and motion.
I think that answer, the last part is best fits here because you're right, it gives the correlation better.
Yeah.
All right, I think that's the last because the first one is just writing the numbers that you gave us and then we do the graph. Yes, and I will continue working on my work on my homework for chapter. I don't know how my other classmates are doing because they don't seem to ask questions, but I don't know.
Well, they do. They ask a few by email, and there's been a few that come on here, but usually I think what they do is they wait for you to ask them and then they listen to the recording.
Really? Well, yeah. But something interesting too, that at the beginning of the class, you said that we will never be riding a car without thinking about physics. And you're right about that. It's interesting that now I get into my car and I just be thinking about physics. And I have learned so much in this class. And I'm happy because it's preparing me for my next, in my next program that I'm gonna be in. But I think this class physics and microbiology should be very mandatory in to graduate, because they teach a lot, I think.
Okay, yeah, I'm on page with
believe
that.
so. I have learned a lot, because this is, I don't know, I have learned a lot, and I have, like I said, I already have a degree, and I can believe it that I am learning so much in this class. But I think I learned so much in this class in microbiology. I didn't like microbiology that much, but I learned a lot, and especially with right now with the pandemic, it helped me a lot.
Yeah.
How to take care of myself, and how to, yes.
Yeah.
Anyway,
yeah.
All right. So I let you be. Okay. So I keep working on my homework. Okay. Thank you, Professor. Bye.
All right.
Bye.
Bye. Take care. All right. Let's see. The rest of you guys coming in. Let's see. I'll check the chat room here. Let's see. Who do we have now? I know a couple of people ran off to math, and they said they'd come back at the third session, or maybe late in the second one here. All right. Well, I don't see anything in the chat room. I don't know if Daniel, you got something for me?
If there's nothing in the chat room, I'm working on chapter 35, 33.
Okay.
And I'm reading the problem, 589 nanometers of light. Does that have any meaning in this, or do we just ignore that number? Because
probably not. The way that's
because it says things surrounded by air, which would be 1, basically.
Yeah, but remember the index of refraction changes a little bit. Maybe I better read that question. But the index of refraction does vary a little bit.
You want to just go through it really fast, because it's
yeah, I do here. All right, so let me write down here chapter 35, number 33, and let me share my monitor.
almost so. Over this past weekend, I ordered a computer, like a PC in parts. So over spring break, I'm going to be putting it together. Almost all the parts are here. I'm just missing my motherboard.
Oh, nice.
Yeah, I'm going to use it for both video games and school.
Okay.
But like one main reason for getting it is right now I'm operating on like a laptop, and with some of the programs I have to run for engineering and like physics and stuff, it like my computer is not equipped enough to handle it. So I'm building a stronger computer so can have flawless school.
Oh, good. Well, you'll learn a lot doing that. That's good. I built a couple of computers, and those days it was a little more common. I guess because these days it almost seems like there's not much of a money savings if you build your own. Where 2 decades ago it was, you could save a lot of money.
I could see that. I mean, for certain things it's a money saver.
Okay.
Other things it's just like you're maybe paying a little bit more, but you're building a stronger, faster computer at the same time. So
okay. Yeah, no, that's good. I had a fun time when building a couple of them and learned a lot. Yeah. And then somewhere
are you talking about your computer you're building, Danny?
Yeah, I was telling him like that operating school wise, my computer just isn't handling it. So I bit the bullet and ordered the parts and like looking forward to doing that over spring break.
Yeah, lots of fun.
All right. Hey, so I'll jump on number 33 here. And it asks us to calculate the critical angle. So maybe as a quick review, let me talk about the critical angle. If you're in some material, and that's the first thing I want to say, the critical angle only makes sense when you're going from in something to out. Because the critical angle does this. Let me say you're in, I'll just put down here glass and to air. That's kind of the easiest thing to build and talk about. But if you have a beam of light and it goes into a faster material, that's why you have to be in something and going to something slower. And usually air is the way to do it. You will bend away from the normal. And so the angle coming in, we call theta 1. The angle coming out, which we call the refraction angle, we call theta 2. And if you are bending away from the normal, and I'll say it again, only if you are bending away from the normal. So only if you are going from slow to fast. So from glass to air, this would work. But from air to glass, it would not work. But if you were to have enough bending so that theta 2 is actually 90 degrees. Something very interesting happened. And it doesn't stay at 90 degrees. Once the beam goes across the surface at 90 degrees, with half the beam in the slow, I'll put a little slow here, and the other half of the beam out in the air where it's fast, it will continue to arch around. And of course, it'll all do this on a microscopic level. So it'll look like a reflection. And so I think one of the things that confuses students when they're working with critical angles is we talk about the refracted beam at 90 degrees, but then we draw it as a reflection. And it kind of throws students off a little bit. They're like, wait, is it going at 90 degrees or is it being reflected? And it's kind of a little bit of both. It bends enough to be 90 degrees. And so that's how we're going to put it into Snell's law. But then once it's at 90 degrees, with half of it in the slow material and the other half in the fast material, it'll bend around and ultimately reflect. So it's probably best to draw it as a reflection, and that's why it's called total internal reflection. But when we go to do the calculation, we do 90 degrees. So watch this. If I put Snell's law, N1 sine theta 1 equals N2 sine theta 2, and we tell ourselves that the refracted angle is at 90 degrees, we can put in sine of 90 degrees, which is just equal to 1. So at this special angle, which I'll call critical angle and put a little sub C, critical angle goes with 90 degrees. So mathematically, this means that the sine of the critical angle is N2 over N1. And I got my first freeze, Well, man, it's a bummer. Keep connected. If I can figure out. I'm gonna fill my phone. Is it warm?
Technology is supposed to make life easier, right?
My phone, yeah. The phone doesn't feel too warm. Accidentally hitting a button. All right. Okay, so where I was mentioning when it got frozen here was that this critical angle can be calculated by the ratio of the indices. And so that's really what this problem is boiling down to. It would say then, okay, so the critical angle would be, and let me just take the inverse sine of N2 over N1. And coming back to this problem, it says the following material, and they give A, diamond, and B, flint glass, and C, ice, but they're surrounded by air. And so I'm going to write this as the inverse sine of 1 over N1. See, because again, N2 is what it goes into. So starting in, and then A would be diamond, B would be glass, flint glass, and C would be ice. So I would need the index of each of those. Now, you started this question, Daniel, with saying, well, does it really matter that they give me the wavelength of 589? And I'll say yes to that, because the index of refraction changes slightly from wavelength to wavelength.
Okay.
In fact, we even kind of mentioned that about the rainbow in the last discussion. And that was called dispersion. So for me to do A, I'm going to need to know what is the index of refraction of diamond, and to be more specific, diamond at that wavelength. And so I need to probably come over here and launch my
So we'll just be referring to chart for those to find the values for that?
Yeah.
Hmm.
Yeah. I don't think they want anything fancy here. And also, and that's why I want to look at this chart here, because there are two charts. One is just kind of the general, what is the index of refraction? And the other one is a more specific graph. And I don't know if we have that for the material. So I say the 289 might matter, because again, I'm not sure we have enough information.
I don't remember seeing that graph chart in chapter 35, but
Okay.
the different indexes of refraction is on page 987.
987. Okay, I see it. So diamond says 2.419. Part B was flint glass, which they list on this chart as 1.66. And the last one is ice, which they list at 1.309. And I might be using those, but let me emphasize, those are the numbers at, oh, maybe this is why. Look at the bottom of that chart, Daniel. It says, note, these are values that are measured at 589 nanometers.
Oh, I see. So that's when 589 nanometers in the problem was like so important.
Yeah, they were telling you that you could go ahead and use that chart. Now, by the way, if you're interested, if you go down to page 992, you will see a figure at the bottom of that page, figure 3521, that shows a graph, and it has crown glass, acrylic, and fused quartz.
Yeah.
Now, that doesn't help us with our problem because none of those materials are the materials that our problem involves. But that's the one I was referring to, that they do have a graph showing us the variation in the index for some materials. And it looks like there's just 3: ground glass, acrylic, and fused quartz. So if, for example, I was using fused quartz at 589, I could either use that chart or go back to that table. But if I was doing it at, say, 400 nanometers, I might want to come back to this chart or this graph on figure 3521. And then as I look over on the graph at 400 and go up, it looks like 1.47. So had they told me it was 400 nanometers and fused quartz, I might try that. But
we also have a formula for going ahead and converting, right? If you're not working with the given wavelength on that chart, right?
Now, which formula are you referring to?
Something, I was looking in our notes. We have the lambda naught over, or lambda of a vacuum over the n is equal to, oh, actually I was wrong. My bad. Is there a formula converting between like different wavelengths there? Or...
Yeah, and that's what I was getting at. There is a formula, and I don't recall it being anywhere in your textbook because it's considered an advanced optic topic. It was discovered by a guy named Crouchy, so it's called Crouchy's formula. You actually will see it in the lab next week, because next week's lab says measure the index for, and I think we do it for 7 different wavelengths. So we try to repeat that graph. And so I'll have 7 different wavelengths and I'll measure the index. And of course, like all of our online labs, I'll be your lab partner and I'll set up the equipment and show you. And then your job then is to put that data into graphical analysis and kind of get that same looking curve that we're looking here on figure 3521. And
okay.
And then Crouchy, and then at the very end of that, the textbook or the lab book, not the textbook, but the lab book says, hey, by the way, Crouchy worked this out. And so try to curve fit it to this little parameter. And they give you Crouchy's formula there.
Oh, okay, cool.
Yeah.
Awesome.
So that was a long way of saying you haven't seen it. You won't see it in the book. You will come across it in the lab.
Cool.
Yeah. Okay, so then to actually then calculate this problem and to get that critical angle, why don't I just put critical angle for the first one, which is diamond, and critical angle for the second one, which was flint glass, and critical angle for the third one, which was ice. I would do, I guess, something like this: inverse sine of the reciprocal of 2.419. Let's see what that gives. So looks like for diamond, we're looking at 24.4 degrees. For flint glass, the inverse sine of the reciprocal of 1.66, a little bigger angle, 37.0 degrees. And then finally, arc sine of 1.309 reciprocal and 49.8. I lost it again. What is it that loves to do that? Disconnect. That'll be. good for me this week. I'm going to look up how to. Hook up or if I can do a direct feed from my camera to the USB. I think I was telling you guys, I tried to look that up one time and it didn't look very like it could be done. And I kind of moved on because I had this connection. Actually, maybe I should also scan my Bluetooth connections. Maybe there's something in there that's a timeout or.
Do you have both Apple products?
I don't, no.
Oh, so sometimes Apple talking to Windows isn't always the greatest.
Yeah, that is true.
Whereas Apple talking to Apple is amazing.
Yeah, that is what Apple does well.
I'm looking into getting a camera for my own desktop that I have. If I find one that works, would you like me to send you a link?
Sure. Although I think my next plan, I just did this right when the pandemic hit, and I go, I'm just going to hook up my phone here, and I kind of liked it and kind of stuck with it. And as you know, last spring we were all just kind of thrown at this at the last with the 1 day notice. Okay, no more in-face classes. But I actually have at our school we have one of these USB. It's called a dot camera. It just shines down, and I mean it's built
the
exactly.
ladybug ones, right?
Yeah, like a ladybug something. Or, yeah, and it just came to our department right when the pandemic hit. We were supposed to swap it out for the lecture hall. And we had just gotten it that week, and so it's still sitting there in the box somewhere in the storage room. And it got me thinking about this last week when this kept crashing. I said, maybe I should go to campus, or the next time I'm at campus, which would be, usually I make the labs on Monday. I'll just I'll grab that ladybug thing. And I probably should try it also because it's probably a wider screen. I'm just using my camera. It's kind of narrow.
It makes sense.
It's basically like one of those overhead projectors that math teachers would use.
Yeah.
Like they'd sit in the center of the class and they'd project on the board. It's just that electronically.
Yeah, that's exactly it. Yeah. Yeah. And that's all I'm doing with my camera. So, now before we leave this problem though, I want to come back. You should notice these numbers. Notice that the diamond has a high index. And that means it's going to have a small critical angle. And so any light that's inside a diamond, most of the light ricochets around many times because only light that is under 24.4 degrees will come out of the diamond. And so most of the light ricochets around many times, where that's not true for ice. And because of that, then the diamond, will spread the light out, the reds and the blues and the greens. And so you get the what you call the diamond look. You get the flashy light, you get the rainbow color, you get the sparkle. Of course, the other thing you get is it depends on the angle that you cut it. And a diamond structure allows for the sharp angles. So you get a small angle where you can also cut the diamond at big angles. Anyways, and it gives it a lot of sparkly. So that's kind of the science behind why diamonds can be sparkly and can flash and can have the rainbow color. Whereas that doesn't really happen. It still happens, but not so much in an ice crystal.
So basically higher the index, lower the angle.
Yeah.
Okay.
Because again, back to this picture, this is the bending of it. And how much bends is the difference between the materials, the index between those materials. So if you really want it to bend around, you want this index to be, the change in your index to be really high. So diamond to air is I think the highest of all materials in the visible range. Yeah. All right, cool. All right, so back over here. Aha, here's my zoom. Good. All right, so what did we just do? We just did 33. And it looks like, all right, John's got one here. Next, number 30, or chapter 35, number 52. Good. Let me put here at 112. Okay. So in case anybody's scanning here, the video will go chapter 35, number 52.
Hello.
Hello.
Hi.
Yeah.
Sorry, I meant number 51. I'm sorry.
Oh, okay, I see that. I didn't read that far. Yeah. Okay. Good. Glad you corrected that. Right.
Sorry.
So, all right, let me change that to 51. I see that in your next one. Sorry, I meant 51. Okay. Good. All right, 51 here. All right, so let me find 51. Oh, good. Another total internal reflection, it looks like, based on the picture here. But let me read it here. It says a light beam in figure 51 strikes surface number 2 at its critical angle. Determine the angle of incidence theta 1. Okay, so we've got a equilateral, which also means equal angular prism. And that wasn't quite perfect, but I'm going to go with it. All right. And then they show that this is 60 degrees. So that's our equilateral triangle. And the first surface, they say the light comes in at theta 1. And they don't actually say if we're in glass, so I hesitate to say if this is a glass prism. But whatever the prism is, it would have a higher index than the air, so it would bend towards the normal. And I don't have much room to write, so I'm going to put theta 2 and point to it. So that angle would be theta 2. But then as it crosses inside of this prism, they say it hits at an angle, and I'll just point to that one, of 42 degrees. And they even go on to say that that is the critical angle. And gonna lock me up again, okay? Kind of curious. Seems to freeze when this little icon goes away. It's called air host. So if I open air hosts, let's see.
Are you going to have an office hours over spring break or no?
Interesting. Okay, I think I noticed something very interesting. Looks like something called air host comes on, and when that shuts off, although I don't know why it shuts off, that's when it freezes. And it air host. All right, well, I'm gonna have to Google what the heck is air host on my Windows operating system. Maybe it has a sleep mode or something. Okay, well, it's probably not that Friday. It's a good question. What should I do?
Yeah, I figured you wouldn't, but I just wanted to make sure. Never hurts to ask.
Yeah, it is a break too. So
yeah.
Yeah, it might be good for you guys to have the break. We're not pushing real close to an exam, so yeah, so
Yeah,
but
still like a week after spring break and then the exam. So
yeah. And but don't hesitate to send me a question or two. I'll gladly make some video solutions. Give me I kind of like those. Those are kind of fun. So keeps me entertained. So yeah, that's what I should say. All right. So coming back to this problem before it froze there, this 42 degrees was, they said, the critical angle. And so if you'll let me go back to the problem we did before, and I'll just kind of repeat, we said if you were writing down Snell's law and you said the light was inside of something. The last problem we did different materials like diamond and flint glass and ice. But if you put down critical angle for the angle coming in, then the critical angle occurs right when the refracted angle is 90 degrees. And so we came up with this little formula for the critical angle. And the reason that's helpful in this problem is because we're told that it is hitting it at the critical angle, which we're also told it's 42 degrees. So they've essentially told us the critical angle. They also said that the prism is surrounded by air, or did they? They did not explicitly say surrounding the prism is air. So maybe I should check the solutions before we leave this one, but I'm pretty sure they're trying to imply that. So I'm going to take N2 to be equal to 1, which will then allow me to figure out what the index is, number 1, which represents the prism. So 1 divided by the sine of 42 degrees gives me 1.49, which is a common number for glass. So again, this is probably just a glass prism that you would be holding up, in the lab, so it's surrounded by air. Okay. So that's the one piece, and maybe the easier of the pieces, because now if I apply Snell's law, so I'm going to write Snell's law again, but maybe to make some more clarity, I should have said up here, I was applying Snell's law to surface number 2. That's why I ultimately put 90 degrees here, because they told me that it was at the critical angle. But now I'm going to apply Snell's law where the light is coming in, and that's surface number 1. And so coming back up here to where it comes in and doing again N1 as 1, then the sine of theta 1, I don't know theta 1, that's my goal, is find theta 1, goes into the prism, which we now have concluded it is an index of 1.49. And then it's sine of, and I'm just going to put theta 2 here for a moment, because I don't really know what theta 2 is until I do some geometry. So I'm going to come back up here. And so you guys can see it a little better. I'm going to make that 60-degree angle a little bigger. And this coming in is my theta 1, and it bends. And so this is what I'd like to know, that theta 2. Now, again, as you watch this come across, and we draw a normal here, normal, they told us this is a 42. So if I grab my calculator and I realize that, okay, this angle right here plus the 42 has to be the 90 degrees. So 90 minus 42 should be a 48. And then if you look at this, what I'll call a triangle here, these 3 angles, and so counting that one as the third, in other words, the 40 and the 48, and whatever this unknown is, should add up to 180. So if I go 180 and subtract a 60 and also subtract a 48, I'm at 72 degrees. And this was kind of my warning for this chapter, that some of the harder things really isn't the Snell's law and the physics, it's just the geometry of getting back. And in this case, I need to remember that right angles are 90 degrees, and I also need to remember triangles. The angles inside a triangle add up to 180. Now, looking at that 72 and theta 2, right, that gets me to the normal. So those two added together, the 72 and theta 2 got to add up to 90. So if I go 90 minus 72, I get 18. All right, so after doing a little geometry, I can come back to my physics and say, all right, this is the sine of 18 degrees. So then if I go the 1.49 and then go times the sine of 18 degrees, that would be the sine of theta 1. So take the inverse sine And I get 27.4. 27.4 theta 1. And let me jump over to solutions. And, oh, good. And they got the same number. And yeah, they also. Oh, now I like a little better what they did. They did not assume it was air. They left this, I'll change colors. They left this as N2 over N1. Because down here, when you bring this over, you have your N2 over your N1. So you don't have to assume that it's air on the outside and you can still solve it. You just know what the ratio of the indices is. You don't know exactly what they are. Okay. Now that would probably would a little better. Where I kind of assumed that it would be air on the outside. So it turns out no matter what's on the outside, it would work. Which kind of makes sense. That's what they said. It was the critical angle. Okay. Nice.
Thank you.
All right. That was a good one. Who asked that? Oh, Johnny asked that one. Okay. So let's go to another one here, unless you guys have a question on that one. Let's go to chapter 35. How about 37? And what is the time? One.
You want to do Anthony's first? I've already asked a question today.
Oh.
If not, that's cool. I don't really mind, is where I'm at.
I don't, yeah. That would be nice. Oh, my bad. I meant
57.
Oh, you meant 57.
Yeah.
Okay. But all right. No, I'll do. Yeah, that's okay, that's cool. All right, we'll go to Anthony. All right. Chapter 36. Number 61. Okay. But unless this one's really long, I have a feeling we got time before the break to do this one. Definitely got time before the day's over. All right. So now I'll put down the time. Okay. So 1:29. Okay. I'll get myself a new yellow sheet here and say, all right, let's put here chapter 36, number 61. Oh, now that I pay attention, that's the new chapter and a big number. So let's see how hard this one is. This one might be getting to the hard stuff. All right, so chapter 36, okay, number 61 says the following. An object is placed 12 centimeters to the left of a diverging lens that has a focal length of -6. All right, so maybe to help me understand, I'm going to put a diverging lens. I'll even put focal length equals -6. The object is 12 to the left. So maybe I'll put kind of a vertical arrowhead here and put in 12. Okay. Then it says a converging lens. Oh, so we got two lenses here. Of focal length 12 is placed a distance d to the right. Okay, so I'm going to draw a converging lens, focal length plus 12, and an unknown distance d between the two lenses. Okay. find the distance d so that the final image is infinite. Oh, okay. And draw the ray diagram. Infinities are always a little bit more challenging than just regular numbers. But also what's challenging, and maybe this is part of the problem, but I'm glad somebody asked it here today. This will be what I know I'll get a lot of questions next week, is the two lenses. And you probably heard me say in the lab, let's see, was this week's lab the lenses one, real images?
It's refraction lab.
This week's is refraction?
Yeah.
Okay. So the two lenses is a hard one. And we do a lab, so I guess that's next week, to help you with the two lenses. And here's what I'm going to say. And I made the video last week, so you'll hear me say it over and over on the video, that you take the image that is formed by the first lens, that then becomes your object for the second lens. Okay, so watch this. Let me put in 1 over p plus 1 over q equals 1 over f. And for the moment, let me just ignore the second lens. Let's just say the light is coming from the object, going to the diverging lens. And where is the image? And so I can calculate it here by saying, okay, the object is 12 centimeters away. The image position is what I'd like to solve for. And the focal length is a -6. So if I grab a calculator and put in a -6 reciprocal, so that's that one, and subtract, I'm going to bring it over to the other side, a 12 reciprocal, and then take the reciprocal of that, I get a -4. So where is the image? The image is at a position of 4, and it's negative. So one of the challenging things of this chapter is keeping track of what do positive and negatives mean. And in this case, the Q is negative. That would mean if the light goes from left to right, so this is where the right really goes, to the right-hand side. This is the positive side for Q, and the negative is over here. So a -4 would be right about here somewhere. Now, I'll also do the magnification, which is minus Q over P. So this would be the negative of a -4 over a 12. That would be a +4 over 12, which is 1/3. So the other thing I would say is having a magnification of 1/3, it sounds funny because it's a demagnification, means that the image is 1/3 the size, but the first thing I'm going to look at is that it's positive. And so I'll say it again, one of the challenging things about this chapter is keeping track of what is positive and what is negative. Oh, and it looks like I got to reconnect. But with a positive of 1/3, then I know that it is upright and it is smaller. It's 1/3 the size. So I'm going to draw it here like this. Now, before I do the second lens, I'll just do the other part of this problem, which says draw the ray diagram. Okay, so let's see. Maybe I'll draw things in green so that maybe they'll stand out. But with a focal length of 6, it means, let's see, if this is 4, 6 would be right about here on the left side of the lens, and right about here on the right side of the lens. And so it would say that a beam of light try this. Beam of light heading towards the focal length on the left would bend and go straight. Thing like that. And a beam that was going straight would bend out as if it is coming from this focal point. And these two rays then would have the appearance of coming from that spot. That's why we have the image here. And so we would call this a virtual image, because somebody standing on this side, now again, I'm ignoring this second lens for a moment, but somebody standing here would have the light coming out, and in their brains would trace it back to a spot that is on the, what we call the virtual side of the lens, and would be coming from this location. And so that's the effect of the first lens. We got its size, and we got its position. Okay, now let me do the same process. 1 over P plus 1 over Q equals 1 over F. And I'll point out this is what makes the two lens the hard one, because as the light is now approaching this second lens, this lens sees the light as if it was coming from the image that is formed by this lens. I mean, that's what we mean by this lens, right? The real object is back here, and the light was redirected by the lens as if it was coming from this point. So as far as the second lens is concerned, it has no way to know that the light coming from the image of the first one is actually an image versus a real object. It doesn't know. In fact, even the viewer may not know unless they saw things like the lens and had some other information. But if you're just directly looking through the lens and you don't know it's a lens, you would say the object is only 1/3 of its real size, and it's at this position 4 from the lens. You just don't know there's a lens, and you don't know there's a real object over here. And so the way you treat a problem with a second lens is you take the second lens, and the object for the second lens is the image from the first one. And so I like to say the image from the first becomes the object for the second. And that would continue, by the way. The image from the second would become the object for the third. And the image for the third would become the object for the fourth. And so we can have a whole chain of events of different lenses here. Okay. So I don't know if that was the hard part on this problem, but that is often one of the hard problems for problems that have more than one lens / mirror. Now, this one's, I think, even extra hard because the question says to find the distance D between these two. Okay. Find the distance D to the right of the diverging lens so that the final image is at infinity. All right. So at infinity would mean 1 over infinity. Was 1 over F, 1 over P. Now, infinity in an equation often is a pain, but fortunately, 1 over infinity is not. 1 over infinity is just 0. And maybe you could just write big instead, because the image would never really be at infinity, but it might be several hundreds of miles. So 1 over millions of meters is pretty small. And so 1 over big, I call 0. And so that means object distance needs to be the same as focal length. Well, that's a perfect way to answer this question then. Let's come back up to the picture. So this really is saying if you place the object right at the focal length, the image gets formed at infinity. Or you might even say the image never does get formed. You have to keep going further and further out before the light actually merges to form an image. So this would be, in our case, for the second lens, 12 centimeters. The second lens is 12 centimeters. So what we're really saying here is the image from the first, which is now becoming the object of the second, okay? And so the object of the second really needs to be 12 away, okay? So that means from this lens to, and I don't know how you want to call this position. I can call it the image of the first, or I can call it the object for the second. Maybe I should call it the object of the second. But that needs to be 12 centimeters. And we already know from the earlier part of this problem that this was 4 right here. And so from the first lens to the image was 4. So that means the rest of this, the D, must be the missing 8. So that it's 8 and then 4 for a total of 12. And so our object distance would be 12. All right, so there's the answer to our question. We've got to have the lenses separated by 8 centimeters. Now, drawing this ray one is a bit tricky also. But I'll go ahead and give it a try. But if your object is right at the focal point, in fact, maybe before I draw it up there, I'll just draw a single converging lens by itself. If you were trying to draw where the ray goes and your object is actually at the focal, we said you do something like this. The ray that is going parallel hits and goes through the focal point. Okay. Now, the ray, and this is kind of weird to say, that goes through the focal point, but it's at the focal point. So I'm just kind of maybe going to make it kind of a short arrowhead and say it's right there. That one that goes through the focal point and to the lens continues in that same direction. What I'm trying to say is these two rays are parallel in this case. If this was exactly at the focal length. Now, if the object was a little further back, these rays would be converging in. And if the object was a little closer, they would be diverging out. But the hard one to think about is right at the focal point. Right at the focal point, they are parallel to each other. That's a way of saying they would meet at infinity. Yeah, when they meet, that's where the image is. And so two parallel lines do not meet until they get to infinity. And so drawing the ray diagram might actually be one of the hardest things to do when you have your object right at the focal point, because what it does is make parallel light. And parallel light, you know, most people would say parallel light never meets. Well, I'll change that to say it meets at infinity. And so where is the image? Where do they meet? At infinity. All right. So that's what we have here. So trying to draw this is a bit tricky, but I will draw or continue to draw this one that comes in. This is the one that I said would go, let's see if we make the focal length right about here, it would go through that focal point and continue on indefinitely. Now, another one, maybe going through the center of the lens, would be coming from, and remember, would have the same angle, the same pattern as if it was coming from the top here. Right here, this is the image from the first. This is what is being thought of as the object for the second. Of course, really, it came from back here. But if I were to draw this one, it would continue on. And these two would be parallel. And that's why we would say the image doesn't form until these lines meet. And these lines don't meet till you get to infinity. So I like the math part of this problem. I'm not sure I like the ray drawing diagram of this problem. Because drawing ray diagrams when it's right at the focal point, I think can be more confusing than helpful for students. But let me jump back and call up the answer for 36, number 61 here. And see what they drawn. Yeah, actually they did exactly the same rays I did. Yeah, we got them coming through here. And then this one going out. Yeah, of course their drawing looks a lot better than mine. But the numbers agree here, distance equals 8. Okay, nice. I'm good. All right, let me come back to the homework. And swing back over to the chat. Okay, so unless you guys got a question on that, maybe I should say, all right, let's try. Back to Hunter. We skipped over you. So let's see, 35, and then you say number 57. Okay. And we are at 140 now. Okay. So chapter 35, number 57. Hey, you guys saw that email, I assume, I sent last night about 6 solutions to chapter 35, no, 36 that were asked last year.
Yeah.
Maybe you didn't get that far yet.
I saw the email and at least marked them saying that they have a video solution if I struggle.
Yeah, I was working along and somebody had sent me a question and I go, hey, this looks familiar. I couldn't have done this before. And then it dawned on me, oh, we just hit the 1 year mark. I might have done this last spring. And so I looked up what I did last spring and I found those 6 and I go, okay, well, I already made 6 for the next chapter. So
does this mean for the rest of the year, you just have a plethora of videos from last year?
Well, I will have some. I'm not, I kind of remember I didn't get a whole lot of questions. I must have got 6 last time because I did 6. But yeah, so maybe we'll start each chapter with 6 already done.
Cool. Can kind of help you plan around which ones to ask questions for.
Yeah,
or video solution.
But it was also the first time doing it, so I wondered if I should look at it and see. You know, presumably I've made some improvement along the way. I don't know, but this is exactly what I started. I just started doing it. Yeah. Okay. Anyways, let's we'll jump on this one. 57 here. All right. So let's jump back to. Okay, wrong chapter. Okay, back to chapter 35. 57. Okay. So again, I'm going to say the same thing that I said in the other one, that I have a feeling maybe the biggest struggle might be geometry and working with the angles, not so much the Snell's law, but here we go. So 57 says a material have an index of refraction n, is surrounded by a vacuum, so index of 1, and is in the shape of a quarter circle with radius r. So they've got a nice little picture of a quarter circle. Looks something like that. There's a radius of r. And they say a light ray parallel to the base of the material. Okay. So parallel to the base is incident from the left at a distance L above the base. Okay, so the light comes in. And so if I'm doing my physics, I know that that would bend towards the normal. Now, also doing my geometry, and I think this might come into play. If I'm drawing a circle, or in this case, a quarter of a circle, perpendicular to the circumference of a circle is the radius. And so this normal goes right to the center here. And they don't show it in their drawing, but I'm going to just kind of remind myself of that geometry because I think that might be important. Okay. Then it's, of course, bends towards the normal. Then if I draw another Snell's law as it exits, I'm going to draw a normal. It would bend away from the normal. Says it emerges from the material at an angle of theta. Determine an expression. Oh, now expressions are always harder too. So there's no numbers I can calculate for the angle theta. All right, so let's see where this gets me here. Okay. So I do have Snell's law twice. Let me call coming in surface 1 and coming out surface 2. So let me deal with surface 1 first. So I'm going to write N1 sine theta 1 is equal to N2 sine theta 2. All right. Now, they did say it was surrounded by a vacuum. So I can put a 1 here for theta 1 as it comes into surface number 1. And then I have this angle theta 1, which I'll put in my diagram right here. But here's where some geometry comes into play. I'm going to take advantage of, I know that the base is parallel to the light beam, and this diagonal, or this, I guess a transverse would be the better name, which is the normal that goes right through the center, would make this angle theta 1 also. And so these in geometry are called corresponding angles. And I think that's going to be useful. Anyways, this goes into the material, whatever it is. So I'll just put index n. And then it would be sine of theta 2. Okay, now theta 2 is this little thing in here. Now, I think I'm going to do some geometry on these angles, but I want to just kind of focus on the physics here for a moment. So let me look at when the light comes out. Okay. So when it's coming out, it hits this angle right here. And for lack of better word, let me call it theta 3. Because when it comes out, they call that just theta with no symbol. So if I do the Snell's law on surface number 2, so I'll first just call it 1 and 2. But I want to get away from 1 and 2 because 1 and 2 might confuse you with, the 1 and 2 at surface number 1. So let's apply Snell's law to surface number 2. So as we're coming out, we're in the material. So this N1 is a 1. And then we have sine of, and I'm calling that theta 3. And then it comes out into the vacuum. So that's n equal to 1. And so then this is the sine of just theta. Okay, now to answer their question, that's probably what I want right there. See, sine theta. If I just took the inverse sine, I would have it. Okay. All right. Now, let me go back to this equation for surface number 1 because they wanted an equation, an expression. And the general rule of all these kind of problems is to give an answer in the symbols they have given. So as I scan the problem, they have an L for the height of the beam. They have an R for the radius of the quarter circle. They have an N for the material. That might be it. But what I do know is they don't list a theta 3, and they don't list a theta 1, and they don't list a theta 2. So I think my job is to write the theta 1, the theta 2s, and the theta 3s in terms of the L's and the R's and the N's. And so I'll start with theta 1. You might be able to see it right here. If I draw a vertical line, this is where the theta 1 corresponding angle would come into play. Because if you do the sine of theta 1 down here, you would say it is opposite over hypotenuse. Well, the opposite is L, and the hypotenuse is R. So that would be a quick way to convert sine of theta 1 into an L and an R. Now, sine of theta 2. Let me hold off on that. I don't see anything worthwhile quite yet. But this triangle, I'm going to draw in green. And maybe expand it over here on the side. So you can kind of see it better. So this is the theta 2. And this is the theta 3. But remember that this right in here would also be a theta 1. So this would be a theta 1. Meaning this angle is 180 degrees minus theta 1. Now, I don't know if that's going to help me too much, but I want to try that first. So these three angles, theta 2 plus theta 3 plus 180 minus theta 1 equals the three sides of a triangle, which equals 180. So the 180s cancel off, and that tells me that theta 1 would be the theta 2 plus theta 3. Is that helpful? Well, I'm just going to keep working with this. I hope it gets me somewhere. Let me come back. Am I missing a angle? Theta 2. Like I might be missing something about theta 2. Okay, but I don't see anything.
Is
But
there
I
any way to
could-
express it with like n, possibly?
Well, I was kind of hoping, here's kind of what I was thinking, that if I could replace this theta 2 in here with a theta 1 and a theta 3, then with some trig identity, I think I can write it in terms of theta 3. And hopefully get rid of that.
I think he froze up again.
Ah. All right. So I don't see anything pretty. So I'm gonna kind of debate which is the best approach. Solve this for theta 2 or theta 3. Don't really know, but I think I'll go with theta 3. How about that? Let me do this. So theta 3 is theta 1 minus theta 2. And I'm going to use that over here. So this actually becomes n sine, and this would be theta 1 minus theta 2 equals sine of theta. And I guess I kind of like that because I am asked to solve this for theta. So all I have to do is take the inverse sign, okay? But in this case, I need to remember my trig identity. And so let me just think this through. Sine of a plus b is the sine of a times the cosine of b plus then the sine of b cosine of a. Let me just ponder that. I'm pretty sure I'm remembering that right before I go to Appendix B. So if I went to apply this, I would say it's the sine of the first one. And I guess I'm thinking of this as plus a negative. So this would be cosine of a negative theta 2 plus sine of the second, so that's minus theta 2, and then cosine of the first. And that all equals sine theta. Now, I am going to take a little bit advantage of what in your math you called even and odd functions. Cosine is an even function. So cosine of negative theta 2 is the same as just cosine of a positive. So it's technically, when I did the identity, it's a negative, but I can change it to a positive. And then likewise right here, a sine is an odd function, which means that the sine of negative theta over 2 is the same as negative sine of plus. Now, and that's probably actually a trig identity with the minus sign. We can look that one up. All right. But I think we're getting somewhere in the right direction. Because I have an n. And if you remember earlier on, we said, looking back in this picture, sine of theta 1 is L over R. Okay. Now, cosine of theta 2, maybe I should come back up here and just write sine of theta 2. Sine of theta 2 would be L over NR. And cosine of theta 2 would be the square root of 1 minus sine squared. And so I think that's what I want right here. Cosine of theta 2. So this is the square root of 1 minus L squared over N squared R squared.
Can you remind me real quick why it's L over NR?
It's on the first surface, I did Snell's law and I got this equation.
Mhm. Oh, okay, you just rearranged that.
Yeah. So when I moved it up here, I'm just going to move the n to the other side.
Okay, I get what you mean. That I was just lost. Thank you.
Okay. Okay. So now here I have sine of theta 2. So this was the L over the NR. And then this would be cosine of angle 1. Now, the sine of angle 1 is L over R. So the cosine would be 1 minus the sine squared. Now, can this be simplified?
From the solution, it looks like they just cleared out the roots from the denominators by multiplying around.
Trying to see if I can make this square root look like that square root. It doesn't seem likely. Well, I tell you what, I will. There's a little simplification, but not much I see right away. But maybe I should do what you're saying. I'll look at the solution, see how much they simplified it. But definitely an R can come out. So I have an N with an L and an R. And then I just would have the square root of 1 minus L squared, N squared, R squared. Oh, I might want to get a common denominator there. Minus, and I would still have a 1 over N. And then I would have a square root of 1 minus L squared, R squared. That still equals sine theta. Before I look here, I was going to look, but maybe I'll do one more. Let's find a common denominator in this first one, which would be N squared R squared. So that this right here would become N squared R squared with the minus the L squared. And the other square root would have a common denominator of just R squared. Oh, yeah, that's okay. I like this. Okay. Which would then make an R squared minus an L squared.
Oh, you just froze up again.
Oh, bummer.
I know, we're almost there.
It's always at the best part when the movie freezes or stuff like that.
Okay. So this is what I was writing when it froze. I got a common denominator in each of the square roots. And of course, what's nice about that is they're squared, so you can actually pull them out. So this right here would be just an NR, and this would be an R, but with that N makes an NR. So that means I can take, well, I already have one R. When I bring it out, I get another N and a R. which then I'm left with the square root of n squared minus, I'm not, n squared r squared minus l squared for that square root. And here I'm left with an r squared minus an l squared. And good. So there was some simplifying it could do. Looks like an n would actually cancel off there. And so you get an L over an R squared. And I think this is the best we can do. So then we have the square root. And we have an n squared R squared minus L squared minus another square root, which is an R squared minus L squared. And technically that's sine of theta. So I suppose one more step is officially needed here, where I take the inverse sine of both sides. Yeah. And I did this right. I was like, well, no wonder I didn't see anything that made that theta 2 and theta 1 simplify. So looking, and jump back to chapter 35, number 57. They have, boy, it goes for a while. Oh, good. And then they got inverse sine. They got L over R squared. They got square root n squared R squared minus L minus square root. Yeah, good. All right. So we matched. So good. Always feels good when you get to the end and you haven't made a mistake.
Yeah, figuring out the what we were gonna use to replace the angles inside of that, it was like the hardest part for me. I was like, I don't know what to do here.
Yeah, so like I said, I think, coming back to this front page, it's really, it's part of it was geometry, finding out what theta 1 is, and really that was the key. Once you get theta 1, you know what theta 2 is from Snell's law, and then 3 is related to that angle. Now there was, I think, another big step is this trig identity, and then doing this triangle to get a relationship between, angles 1, 2, and 3, and then doing the trig identity. And even then, there's another big one in here that, again, I guess I'd put this more from your trig class than physics class, but once I did the trig identity, I was beginning to panic, thinking that I had to get not only the sine of the angle, but the cosine. And I only knew the sine, but then I had to remember, oh yeah, anytime I know the sine, I really also know the cosine if I do what's called the Pythagorean trig identity. Yeah. So I had to do not only this identity where the sine of two angles, but what's called the Pythagorean trig identity, which says sine squared theta plus cosine squared theta is 1. So as long as I know the sine of the angle, I also know the cosine of the angle if I'm comfortable with square roots.
Yeah. Awesome. Thank you.
Yeah, so a lot of math, a lot of trigonometric math and geometry, and very little physics, but still some physics, yeah. All right, well, that was a good one, longer than I thought, but it took us into our break. So, all right, we'll take our, I guess it'll be about 40-minute break here and come back at 3.
Thanks.
All right, guys, see you soon.
Thanks.
Mhm.